Okay, so how is everyone today? Good. Okay, so the place we left it last time is we were talking about division. So specifically we had noted that when we want to compute quotient and remainder, the way we originally talked about it is we said, okay, we'll take one handful of M&Ms at a time. So for example, for the program that we wrote, we named it quo rem, and then we wrote two different versions of that. When we asked it to divide, say 2370 by 7, when we did that, more or less the state that we ended up keeping track of was something like this, that there were 4 variables, A, B, and Q, and R. And we said, okay, we want to divide 2370 by 7. And the way we'll do that is we'll start out by saying, okay, currently I've taken away no groups. So Q represents the number of groups we've taken away. Then we ask for each step, we ask, is it possible to take a group? Which is equivalent to asking, is the group size less than how many there currently are? Yeah. So what we'll do is take away 7 and get 2363. The group size is still 7, but we've taken 1 away, so we increment the quotient. And then we do this in a painstaking way. So the next one we'd ask, can we still take away 7? The answer is yes. So now it would be 23 and then 56. The group size is still 7, but we have 1 more quotient. Then we ask, can we take away another one? Yeah, we can. So it would be, the next one would be 2349. The group size is still 7. We increment the quotient. And if we wanted to write this all out, you can imagine it would be a very tall table, and if we wanted to write it all out. So I'll just elide most of that. So getting out my calculator here, my calculator reports to me that 2370 divided by 7, including the floating point, is 338.57. Okay, so it will come to pass that this is 7, and the quotient has become 337. We still don't know what the remainder is. But the current number of M&Ms will be 11. And then we ask ourselves one last time, is it possible to take another group, which is to say, are there greater than or equal to 7 M&Ms? And the answer is yes, because there's currently 11. So we take away 7, and then there's 4. The group size is still 7. Then we have 338. And now we ask ourselves, okay, is it still possible to take a group? No, it's not possible. So then that means that that's the state of that variable is 4, this one is 7, this one is still 338, it doesn't increment, and what, as a result of making the conclusion we can't take away anymore, R now gets defined for the first time in the computation. So what's R?
R is what remains. What's left of A?
Right. So these two items here are the answer, in a sense, that we were after. Okay, now we alighted the majority of the table, right? Approximately how many steps did this take? About 338 steps, right? If you don't include the stuff that happened right at the beginning and the stuff that happened right at the end. The number of steps that it takes is essentially the size of the quotient. So because the quotient is 338, that means that it takes approximately 338 steps. So when you do this in grade school, this is not how it's done at all, right? You don't just slowly take away 7 at a time, except at the beginning when you're first learning how it works. So in grade school, so that's sort of the trivial algorithm that we talked about. In grade school, you do it like this. You have, again, divide 23 by 7. So the way you write it is like this, with a little house. And then because you're taught this in grade school, at least my teacher said something like, you know, okay, 2370 is in the house, and 7 is outside the house, and 7 wants to come in. So you look at the leftmost digit, which is a 2, and you ask, how many times can 7 go into 2? 0 times. So usually what the teacher says at that point is they say, okay, let's take another digit. But to be perfectly clear, I'm going to write a 0. I'm going to write a 0 above the 2. Then I'm going to take away 0, right? I'm going to subtract 0. And then now I'm going to consider two digits. So now we're considering 2 and 3 and interpreting it as 23. How many times can 7 go into 23? 3 times. So you write a 3 vertically aligned with the 23, and then that 3 realizes, oh, I'm in a long division problem, and in despair, I'm going to jump off the house. But the 3 jumps off the house and hits the 7 on the way down, multiplies to become a 21. You write that 21 right here, and then subtract. Of course, you write 21, usually, that's the way they write it in grade school, but do understand that that's not 21, that's actually 2100. That's what that actually is. So I'm going to write 2100. Because I know that we wrote 3 there, but that's not really a 3, that's really a 300. Okay, so then we do the subtraction, and we get a 2 and 7 and 0. Of course, there's a 0 right here. So you usually don't write that, but I'm going to write it. Because that number being 0, that's the signal that you did this right. If that leading number was not 0, that would mean that you could have taken another 7. Okay. Fine. So now what it is that now 27, actually 270 is in the house, but we're only going to consider 27. And 27 is in the house, 7 is outside the house, and 7 wants to come in. So how many times can 7 go into 27? 3 times, right? So we write another 3 that's vertically aligned with that 27. And then this new 3, in despair, realizes it's in a division problem and it jumps off the house. It hits the 7 on the way down. You multiply those together, you get 21. So we'll write 21. But do understand that that's not actually a 21. What is that actually? It's actually a 210. So I'm going to write a 210. And then you subtract those. The leading number is 0, and then you get a 6, 0. Again, under normal circumstances, obviously, you don't write 60 as 060. But I'm pointing it out that the fact that that leading number is 0 is the signal that you did this step correctly. Fine. So now 60 is in the house, and 7 is outside the house, and 7 wants to come in. How many times can 7 go into 60? 8 times. So you write an 8 up here, vertically aligned with the rightmost digit you were considering. The 8 jumps off the house, hits the 7 on the way down, multiplies to become a 56. We do the subtraction. I said 56, and then I'm not sure what happened there. I think I said 56 while I was looking at the 7. So 56. Good. So then the leading number is 0, and then we have a 4. Okay, and then there's, and note it, and when we wrote 56, did we mean 56? Yeah, right. As opposed to when we wrote 21, we really meant 2100. And here when we wrote 21 again, we really meant 210. But when we wrote 56 here, we really did mean 56. That really was a 56. So that 4 really is a 4, and not like a 40 or a 400 or what have you. So now, finally, 4 is in the house and 7 wants to come in. How many times can 7 go into 4? 0 times. And at this place, the algorithm terminates, and you come to the conclusion that the quotient is 338, and the remainder is 4. Of course, that's exactly the same answer as the one above. However, we can write the entire state of the algorithm here on the page in a relatively compact form, whereas we had to elide, on the order of 325 steps to get this one on the page. So here's what we're going to do today. We want to figure out how can we do this. Specifically, how can we convince MATLAB to do this? Okay, so does everyone understand the idea? Okay. So now I want to convince you that, so you can teach that long division algorithm to children, and many of them can do it quite reliably, but my experience tells me that most adults don't really understand exactly what they're doing, even though they could very reliably reproduce the procedure. So now let's think about it very carefully. So this will be long division in base 10. So I'm specifically saying in base 10 because, of course, as a culture we count in base 10, but there's nothing magical about base 10, and honestly the only reason why we count in base 10 is probably because we have 10 fingers. There's probably no other reason than that. Incidentally, what base do computers count in? 2. At any rate, whatever base that you're in, we're going to have the working assumption that multiplying or dividing by the base is very cheap. For example, which number would you rather, suppose I gave you 2370. and I said, I want you to multiply it by this other number. Would you rather multiply it by 1, 2, 3, 4, or would you rather multiply it by 10,000, which is much bigger than 1, 2, 3, 4? 10,000, right? Because that's cheap, because in the end 10,000 is an exponent is 10 to what exponent? 4, right? So multiplying 2370 by 10,000 is equivalent to just shifting the point 4 positions to the right, whereas multiplying by 1, 2, 3, 4 is a little bit complicated. Okay, so we're in base 10, so I'm going to take it as given that multiplying or dividing by 10 is trivial. Okay. So suppose that we want to divide, again, 2370 by 7. The grade school algorithm starts by considering the leftmost digit. But let's try and figure out what that means, because there is no MATLAB command or punctuation that means start by looking at the leftmost digit, right? There isn't such a thing. So the question is, the first question we need to ask ourselves is what exponent in for 10 to exponent n do we want? Okay. So conceptually, I'll write it like this. We have the following choices. We want to ask ourselves, because there's currently 2370, is it possible for us to take away 7? Could we take away 7 right now? Yeah, because there's 2370. Okay, what if we multiply 7 by 10? Well, that'd be 70. And remember, we're considering multiplication by 10 to be cheap. So right now, is it possible to take away 70?
Yeah.
Yeah, we could take away 70 right now. Okay. Well, maybe we'll get super lucky and we could take away even multiply by, right, even another power of 10. Is it possible to take away 700?
Yes.
Ah, we could do that. Oh, we're getting luckier and luckier. All right, is it possible to take away 7,000?
No.
No, that'd be too much, right? That corresponds to saying that if this were the choice, we'd be saying that n is 0. The exponent that we can use is n equal to 0. This one is n equal to 1. This one is n equal to 2. And this one is n equal to 3. In the sense that 7 is 7 multiplied by 10 to 0. 70 is 7 multiplied by 10 to 2. 700 is, wait a second, 10 to 1. 7 multiplied by 10 to 2. And this one is 7 multiplied by 10 to 3. So the answer to this question is that, the n we were looking for is 2. We were looking for 2. All right. The second question. So the quotient is 7, but what we're doing is sort of a shortcut. We're saying, not the quotient, the divisor is 7, but what we're doing is a shortcut. We asked, well, can we take away just 7? Yes. What about, can we take away 10 sevens? Yeah. Can we take away 100 sevens? Yes. Can we take away 1,000 sevens?
Yes.
No. No, we can't take away 1,000 sevens. But we can take away 100 sevens. Now the question is how many times can we take away 100 sevens? So, how many 700s can we take away? Okay, well, can we take away, is it the case that we can only take away a single 700 from 2370?
You can take more.
Right, well, okay, can we take, I agree. Let's ask it that way. Can we take away a single 700? Yes. Okay, well, we can add, because remember we defined how to add things. Can we take away 2 700s? Yes. Can we take away 3 700s? Yes. Can we take away 4 700s? No, we cannot. So in principle, this first procedure could have gone on for an indefinite amount, which is to say that when you're finding the exponent, in principle, the exponent could be any value, right? It turned out to be 2, but in principle, it could have been 2 million. By the way, that would be a number that's just inconceivably large, right? That would be a number with 2 million zeros. Such numbers in practice don't occur in the universe. In practice, here's an extremely large number where the universe is concerned. How many protons are there in the universe?
Is it the mole?
As an estimate. No, so mole is an interesting number, and it's very big. But the number of protons in the universe is even bigger.
Is it 10 to the 100?
It's less, actually. It's 10 to the 80. So as far as we can tell, if we could individually count the number of protons in the universe, it would be a number that has about 80 digits in it. Okay, so what I'm saying is that in principle, this step could go on forever. Well, not forever, but arbitrarily long. But in practice, for all real numbers, for all numbers that you will see in your life, this one's going to take on the order of at most 80 steps. Probably more like 6 steps. Right? Good. So now how many steps could this take? 9. It couldn't possibly take more than 9 steps. It couldn't take more than 10. Because if you found yourself taking more than 10 steps, then what would that indicate? That you didn't do the first step correctly, right? Okay. So here we go. This is saying, what the interpretation of this step is saying that the question is, do we need to take 1 7 times 10 to the 2? Do we take just one of them? Do we take 2 7s times 10 to the 2? Do we take 3 7s times 10 to 2? Or do we take 4 7s times 10 to 2? So here, how many can we take away? We'll call this how many, and we'll give it a name. How about C? So this would correspond to C is 1. This would correspond to C is 2. This would correspond to C is 3. And this would correspond to C is 4. So the answer to this question is what? C is 3. That's the answer to this question. So now that we've done that, we subtract. Specifically, we've established that 21 is the 2100 is the maximum we can take away, and that corresponds to incrementing the quotient by what?
By C.
Not by C.
C times 7 times 10 to the 7.
C times 10 to the n, not C times 7 times 10 to the n, right? Because taking away 2100, that doesn't correspond to incrementing the quotient by 3. It corresponds to incrementing the quotient by 300. right? So now subtract. So we get 2370 minus 2100. The new result is 270. And now we're going to increase the quotient.
Wait, you said increment. Do you mean decrement?
The quotient is going up.
Oh, okay.
So increase the quotient. And we're going to increase it by c multiplied by 10 to n, which is to say, because we established that n was 2 and c was 3, that's 300. Okay, so that means that the quotient is going to be at least 300. Now, of course, this is the third time that we're answering this question today. We know that the real quotient is 338. Okay, so but at this point we know that the quotient, we know in the context of this question that the quotient is at least 338. So now here's the thing. This question, we don't need to answer this question, we don't need to ask this question again. Because there's no way that we could use an exponent of size 2 anymore. It's not possible. Because sorry?
It's just n minus 1.
Right. So now what exponent do we need? Right. So what exponent? We just need to use one less than the current value. So the current value is 2, so we're going to take n as 1. So now what that's saying is that, okay, 100 is too big now, so which is to say we can't take away any more 700s, but perhaps we could take away what? Some 70s. Maybe we could take away some 70s. So how many 70s can we take away?
Is this also C?
Yes, now we're finding C, a new C. Right. So, well, the question is the current the number of M&Ms is at the present time 270. So the question is well, could we take away 70 M&Ms? Yeah. Could we take away 140 M&Ms? Yes. Could we take away 210 M&Ms? Yes. Could we take away 280 M&Ms? No. So the answer to that sequence of questions is that C is what? 3. So this was a question, so this first question was, is C 1? Maybe. But the answer was it's at least 1. Here, the answer to that question is that C is at least 2. When we asked, can we take away 210, the answer was C is at least 3. And then when we asked this question, is C at least 4, the answer was no, it's not. It's too big. So the answer to this question is C is 3. Okay, so that means that now we're able to take away how much? So specifically, we're going to subtract C multiplied by 10. Wait a second. 7 multiplied by C multiplied by 10 to exponent n, okay, which is 7 multiplied by 3 multiplied by 10, because n was 1. So I'll write 10 to 1, which is how much? 210, right? So we'll do that. We do that 270 minus 210. So that means that there's 60 left over. Okay, so then notice that the amount left over, 60, necessarily is less than 70. Because we just got finished asking how many 70s can we take away. If this number that we had written down was 70 or greater, then that would indicate that you'd made an error. You didn't answer the question of how many 70s you can take away correctly. So we can't take away any more 70s. Now what are we going to ask? How many 7s can we take away? Okay. So now the exponent is now n equal to 0. Exponent is 0 because we decrement the exponent from 1 to 0, and then we ask how many 7s can we take away? Oh wait, we forgot to increase the quotient, right? So this one's 9 and this one's 10. So the current value of the quotient is 300, and we established that we were able to take away 3 70s. But the thing is that we're interpreting 7 to be 7 times 10 to 1. So really that means that we increment the quotient by 3 times 10 to 1, right? Which is 10. So we'll increase quotient. By c times 10 to n, which is 30. So the new quotient becomes 330. So that means that at this time, we're not exactly sure what the answer is going to be, but we do know that the quotient is going to be at least 330. And again, because this is the third time we've asked this question, we know that the real quotient is 338. All right. Now how many 7s can we take away? Okay, so then what's left is 60. So the question is well, can we take away at least 1 7? Yes. Can we take away at least 2 7s? Yes. At least 3 7s? Okay, so again, I wanna ask this step. How many 7s can we take away? How many questions do we need to ask to establish the answer? Well, we know it's going to be h. But what I mean is that in principle, every single time we're asking, how many questions do we need to ask?
You ask until you go over and then take 1 step back.
I agree. And so my question is, how many can that conceivably ever be?
9.
9, right? We have to ask 9 questions, at most 9. Why can't it go over 9? Because that's a 10, right? Okay. Could we do 28? Yeah. Could we do 35? Yes. Could we do 42? Yes. Could we do 49? Yes. Could we do 56? Yes. Could we do 63? No. The answer is no. And of course, this one corresponds to C is 8. So the answer to that question was that C is 8. So then what do we need to do now? We need to subtract. Subtract 7 multiplied by C multiplied by 10 to exponent n. Okay, so then at the present time the value of C is, well, so this will be 7 multiplied by 8, and then multiplied by 10. What's the current value of n? It's 0, and 10 to 0 is 1, so that's 56. We make this subtraction. 60 minus 56 is 4, and now we can make our answer. The reason why no further considerations are necessary is because we know that the exponent is 0, which means that it's not possible to decrease the exponent any further when you're dividing among the naturals. Okay. So, as a result, we can make a conclusion that the quotient, well, we had to increase the quotient. So this one's 12. So we increase the quotient. The amount that we increase the quotient by is how much? By 8. Right, c times 10 to exponent n, which of course is 8 multiplied by 10 to exponent 0, which is 8. So the new quotient is 330, and then plus an 8 is 338. So the quotient is 338, and the remainder is 4. Good. So now, this was kind of a really tedious way to sort of write out the computation by hand, but the hope was that as we were writing it out by hand, you were starting to get a sense of how you could convince MATLAB to do it with functions that you write. And then the only things that are permissible are multiplication or division by 10. We'll consider those to be permissible because we're calculating base 10. And then you're allowed to add and subtract. That's it. Add, subtract, that's permissible. And multiply, divide by 10, that's permissible. But nothing else. Okay. So the first step, before we had sort of done really gotten going, we needed to ask, from 2370, can you take away 7? Yes. Can you take away 70? Yes. Can you take away 700? Yes. Can you take away 7,000? No, you cannot. So we need to write a function that figures that out. Okay? So suppose that the question is that we want to divide A by B. And the first thing we want to do is we want a function to compute n from the previous page. All right. That is to say, we want n, a natural, such that such that what? So let's describe it as good as we can. Okay, b times 10 to the n is less than a, and is the maximum of all such n. In fact, it's not less than. Or equal, right? Less than or equal, and n is maximal. Okay, so that means that the signature of the function is that it takes two natural inputs, a and b, and produces what? A single natural output. So its signature is two natural inputs and a single natural output. And then conceptually, this one is the dividend, the thing that's being divided. This one is the divisor, and this one is n. So then, strictly speaking, actually, it's not really naturals cross naturals to naturals. We need to make one minor modification. Because again, this is division, and can't divide by 0, right? So then really what we mean by the second argument, we mean, I'll write n star to mean the naturals which are non-zero. Okay, let's give this one a name. Let's give the function a name. How about quo underscore rem underscore 10 underscore n. So meaning that we're going to compute the quotient and the remainder in base 10, and now we're computing the n. Okay, it takes two arguments, a and b. How will we do it? So I claim that the way we're doing it, you know, first we're considering exponent 0. Right? We consider exponent 0, and then if we can do better than that, we do exponent 1. If we can do better than that, we do exponent 2. So I think we'll take the same trick as before, and we'll have a function that takes one more argument. Takes one more argument. I'll say that this is defined as quo rem 10 n, and then we need to give it a new name. How about underscore 0, the one that actually does the work, a, b, and because the first exponent that we consider is 0, we'll initialize it with 0. So conceptually, this is the first exponent to consider. A, B, 0, yes. So now, if that's the case, we need to define that function. All right. Quo rem 10 n 0 of a, b, and n. Okay, so that means that we want to divide a by b, and furthermore, we're gonna have a go. We're gonna have a try with exponent n. So here we want to write a function that's asking the question, can we use n? So the answer to the question is either yes or no. As a result, how many clauses should this function have? It should have 2 clauses. One of the clauses is going to be that the answer is yes, and in such a case, there's more work to do, and one of the questions is the answer is no, which means that there's no more work to do, essentially. All right, good. So what question do we need to ask? Okay, good. So if b times 10 to exponent n is less than or equal to a, what does that mean? That means that we need to keep going with n plus 1. So I've got to write this diagonally now. So quo rem 10 n 0 with a. That is not going to work. So I'll write a vertical line to distinguish the 2 clauses. So that's the guard, and if that's true, then we're going to do quo rem 10 n 0 with the same a and b, but we're going to try the next exponent, n plus 1. Okay, so supposing that's false, that's the case where we can actually compute the answer, What's the answer? It's not n. It's n minus 1, right? It's n minus 1. It's the previous exponent. Because if the answer to this question, this question conceptually is, you could ask it like, is n too big? So if n is too big, then we can continue. So in fact, we can do even better. We can do one step better, right? We could start with 1, because that would be asking, that's a minor optimization of saying that instead of asking when you're dividing 23 by 7, instead of asking first, can you do it with 7? That's saying, now let's first ask about 70. Could you take away a 70? If the answer is no, you can't take away any 70s, then, well, I guess you can just take away 7s. So we can do even better. Good.
Would we have to list the third variable as n
I'm not sure I understand your question.
and not 1? Would we have to list it as
Here?
n and then state that n is 1 to start?
Well, this is a different function than that function. So we're just saying that every time you call this function, the only thing that it does is it calls that function and starts it with, and always calls it with the third argument as 1. That's what it does. Okay, so then let's do this real quick. Let's do it real quick. So how about some smaller numbers so that, no, it won't be too bad. I'm going to call this just q, and the other one q0, so I don't have to write all that out. So suppose that we call q of 2370 and 7. Well, the first thing that q is going to do is it's going to call q0 of 2370, 7, and what's going to be the first argument? 1. So then, well, that means that conceptually what we're asking is that this is asking the question, can you take away 70? Because that's saying 7 times 10 to exponent 1. 10 to exponent 1 is 10. 7 times 10 is 70. Can you take away a 70? The answer is yes. So that means that there's more work to do. So then it will in turn call 2370, 7, and 2. And then conceptually, what question is this asking? Can you take away 700? And the answer is yes, you can take away 700. Then the next thing that will be called is 2370, 7, and 3. What question is this asking? Can you take away 7,000? Can you?
Oh, no.
The answer is no. As a result, we have determined the exponent. We have determined that 3 is too big, and as a result, the answer is 2. So we figured out the exponent. Good. Any question about this one? Okay. Don't worry, these will be scanned and posted. But the idea is that you have to write a function to compute the exponent. So what's the next thing we need to do?
Find C.
Right. We need a function to compute C. All right. We need a function to compute C. So now this function will be, in fact, it has 3 parameters. So what's currently known, are A, B, and N. And what we want to do is we want to compute C. So that means that the signature of this function will be naturals cross non-zero naturals cross naturals. And then what does it produce?
Natural.
A natural. But in fact, we can be even more precise than that. In fact, there's only 9 possibilities. What are they? 1, 2. It couldn't be 0, right? Right. So, in fact, the possibilities are 1, 2, 3, 4, 5, 6, 7, 8, and 9. There's no other possibilities. So we can be quite precise about it. Fine. So then, a reasonable name for this could be something like quo rem 10 C. How about that? So it's the thing that wants to produce C. All right. So its arguments will be A, B, and N. And because we want to compute C, because we have to keep track of C as state, what are we going to do? We're going to make another function that includes all of these arguments and also the C. So, okay, quo rem 10 C 0. So it will have A, B, N, and what do we need to initialize it to? I think we can do even better.
2.
We can probably initialize it to 2, right? Because we're going to ask, essentially the question that we're asking is the C that we have too big? Is it too big? And the only possibilities are 1 through 9. As a result, we can start with 2, because if 2 is too big, then we know the answer. All right. Then we need a reasonable definition for this. Quo rem 10 C 0 A B N C. So while you're thinking about that, I want to, in the first place, want to remind you that all of these functions that we're defining are for division in base 10. Calculations are all occurring in base 10. Now, there's this many possibilities for computing C in base 10. What if it had come to pass that instead of having 10 fingers, we had 12 fingers? There'd be 11 possibilities, right? It's almost for sure that we have an even number of fingers at any rate, because bilateral symmetry is essentially guaranteed, right? So I have difficulty imagining a situation where we could have an odd number of fingers. So if we were counting in base 12, there'd be 11 possibilities. If we were counting in base 20, there'd be 19 possibilities. So now, what base do computers count in? 2. So when computing the coefficient, how many possibilities are there? 1. No, it's not 0 and 1. Just like because there's 10 digits in base 10, it's always going to be 1 less. So there's 9 choices here. If we were counting in base 4, there'd be 3 choices. If you're counting in base 2, there's just 1 choice, which means that when you're doing this process in binary, you don't even need to do this step. This is not even part of it. So the existence of this function is purely an artifact of counting in base 10. All right. So now, again, this needs to be a function with 2 clauses. One of the clauses conceptually means that we need to go further, and the other one conceptually means we've gone far enough. So what thing do we need to evaluate to figure out which, whatever the case is? So I want some inequality. Okay, good. So c times b times 10 to exponent n less than or equal to a. So that's logically the test of whether or not we've gone far enough. And then to translate it back into a couple pages ago, before we were trying to be so precise, this is the point where we were saying, okay, can we take away 1 700? Yes. Can we take away 2 700s? Yes. Can we take away 3? That's what we're doing here. Okay, so then if it's possible to take away c 700s, then we need to ask ourselves whether or not it's possible to take away c plus 1 700s, because maybe you can. All right. So that means that there's more work to do. So we need to call quo rem 10 c 0 of a, b, n, and c plus 1. So that means that we need to try some more. Here, the alternative to this being true means that no, there is no more work to do. So what's the answer? C minus 1. So let's do a quick evaluation of this just to try it out, just to see what it's like. Except instead of writing that, I'll write capital C or something. So capital C of 2370 dividing by 7, and we'll say that we've determined that the exponent is 2. So that means that we're asking about not 7s, not 70s, but actually 700s. And we're trying to answer the question of just how many 700s can we take away. So the first question, at least the way we've defined it, the first question that we ask, so we need to call the function that actually does the work C0. So 2370, 7, 2, and 2. So what we're asking, conceptually, what is that asking? Yeah. Can you take away 2 700s? Yeah. And the answer is yes. You can take away 2 700s. All right. Well, can you take away 3 700s? Yes. Can you take away 4 700s? No, that's too many 700s. So what's the maximum number of 700s you can take? 3. And of course, that's in agreement with what we wrote on the previous pages. Okay, so now what do we need? Yeah, now we kind of need a function that orchestrates all these things together, right? So now each of the independent steps we know. We know that we know how to compute the initial n, and given that we know, that is to say, the initial exponent, and given that we know the exponent, we know how to compute a c. So that means we now finally need a function to orchestrate all of this together. Okay. So now the function that ties all of this together. All right, so we'll call it quo rem 10. So in particular, we want a function that takes a dividend and a divisor, and then provides the quotient and the remainder. That's what we want. All right. So its signature is what? Right. N cross N star. Any kind of dividend, but must have a non-zero divisor. And what kind of thing does it produce? Naturals cross naturals, right? Two of them. Why two of them? Q and R, right? The quotient and the remainder. Also, strictly speaking, do remember that Euclidean division is nice in the sense that the remainder is natural, but even Euclidean division tells you something even stronger. What must be true about the remainder? Less than b, the dividend, right? Which is to say that, for example, when you divide by 8, there's exactly 8 possibilities for the remainder, 0 through 7. It couldn't be. There's no other remainders permissible. So sort of strictly speaking, do understand that one we could try and be really more complicated and say, well, it's naturals with the additional condition that it's at most one less than this one. Okay. Good. So quotient, remainder in base 10 of A and B. So it takes 2 arguments. But in fact, while the procedure is going, what did we need to keep track of? Right, we needed to keep track of C and N. Well, and specifically, sort of, we also needed to keep track of the quotient, right? Because we were saying, we've got to increment the quotient. So we're going to need at least one more argument to keep track of the quotient, and in fact, we're going to need one more argument to keep track of the exponent. Okay. So, this one's going to have to call, its own auxiliary function. So quo, rem, 10, and I'm just using the convention that underscore 0 is the one that actually does the work. All right. So it still takes A and B, the dividend and the divisor, and I'll say that this first argument is Q. It is going to represent Q. So when the quotient begins, when the process begins, what's the quotient? 0, which is to say, we haven't taken anything away yet. Okay. So this should be 0. And then the next argument, I'm going to say, represents n. Represents n. So we need to how will we initialize that? Now you can't initialize it. So isn't it the case that we know how to do it?
What do you want?
Yeah, we use that function that we defined, right? That was the whole point. So then. Right here, we're going to say that this is quo, rem, 10, n, and then how do we call it? With A and B, right? Who, in a sense, it's like, who cares, right? That's the one that knows how to do it. I don't even know how to do it. This one. I have no idea, right? Let that guy do it. Okay, so there's 4 items. Quo, rem, 10, 0, and then the arguments are A, B, Q, and N. So what that means is that, okay, we're in the thick of it, and we're trying to compute all these things. At the present time, we've taken away Q items, and we're considering what's happening at exponent level n. So how did we know that the process stops when we were doing it a couple pages ago?
When it was too large.
So like, let's imagine here for a second. Suppose we want to divide, say, like 10,000 by 7. So the first question, in a sense, that we're going to ask, you know, we want to compute the exponent, and we ask questions that are logically equivalent to, can I take away 7? Well, what about 70? Yes. What about 700? Yes. What about 7,000? Yes. What about 70,000? No. So that means that the process is going to, in a sense, start with exponent 4. That's equivalent to when you're in grade school and the teacher says, you're looking at the leftmost digit. What that's doing, that's saying, what exponent am I supposed to be using? That's what it's doing. Okay, so it starts at exponent 4. Then once you've exhausted exponent 4, you move on to what exponent? 3. And once you've exhausted exponent 3, you move on to 2. And then once you've exhausted that one, you move to 1. And once you've exhausted 1, you move on to 0. And then that's when you're done, right? So exponent 0 has something to do with telling if you're done, right? Because once the exponent is 0, there's no further work to do. All right. So how do we do it? How do we do it? Let's think about it here. How can we do it?
You first want to establish your n, correct?
Well, we have n. So
You want to think of special cases.
we're in the middle. We're in the midst of it.
So what if like b was 0? Can we just say like drop out a
B can't be 0.
So should we like write a thing that says if b is 0, drop out an error?
Well, I mean, you'll have to do that in an actual program.
Oh, I'm just saying. Well, I'm just going over like special things. And then if a is 0, the whole thing is 0.
You do b times 10 to 10, you would add that to q. Just,
I like that, right? You've got to do something. You've got to do something like that. So let's check. So what if the case? What if n is 0? That's possible. That would mean that this is the last step. We're not going to do anything else after this, right? Okay. If n is 0, then we need to compute the quotient and the remainder right here. So of course this is like the output q, right? So I'll call this like q prime and r prime, and the input we have a quotient currently. So that means that the output quotient is the current quotient, whatever it is, and how much more?
So what times
Plus just c, right?
oh, plus
Plus c because n is 0. So this would be plus. Now, if only we had some kind of function to compute c.
But we do.
Oh, but we do, right? So then this would be plus, quo, rem, 10, c, and then what arguments does it need? A and B, right? Whatever the current values of A and B are. A and B.
Wouldn't it be AB 0?
No, right? Because this one in turn will initialize it correctly.
But we define Q row, Q quo row times C and AB.
Oh, we did? Ah, I think I see. Yes, I agree entirely. My mistake. So I'll write n, and of course n is 0. Good. So that's the quotient. What's the remainder?
Is it what's left of your subtraction?
Right. So then that means that we came in with A, so the remainder is A minus how much?
B times.
B times A to the n.
Right, it'll be B times that. So B times C. So we could make this look slightly nicer and say that this is that. And then we could say where C is equal to quo rem 10 C ABN. Okay, so that would mean if we find ourselves in that position, there's no more work to do. So if n isn't 0, that means that there is more work to do. All right. So what do we need to do? We've got to recurse. We've got to recurse, and we've got to do what? We've got to recurse to what arguments? So we need four different arguments. Two of them are easy. No, A requires a slight calculation.
We got A minus N minus 1.
B is the same, right? B is always B. It's constant during the computation. What are we going to do with n? What's the next n to consider? N minus 1. The quotient, we're going to have to increase the quotient, but you've got to remember what exponent level you're at.
We're out of time, President.
We're out of time? Okay. So I'll leave it as a cliffhanger. See if you can figure out what the correct arguments are. So have a nice Thursday.